Hey everybody, this is Larry. This is day 26 of the January Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about today's problem. I hope everyone's doing well. It's January. I don't know, maybe I'm trying to mix it up a little bit. Today's problem is path with minimum effort. I record and do these problems live. Hope everyone's doing well, stay healthy, if you have an opportunity, take care of yourself. And if you're fortunate that, that's good, then, try to take care of other people around you. Okay, so today's problem is path with minimum effort. You are a hiker preparing for an upcoming hike. I actually do hike a lot, so that would be me. But it is way cold here in New York in the winter, so not anytime soon. I did a bit of hiking in Hong Kong though, but that was a while ago. Time flies. You're given heights. Anyway, sorry. You start in the upper left cell and you go into the bottom right cell. Okay, up, down, left. Oh, up, down, left, right. Okay. I thought it was going to be one of those that you could only go down and right, to be honest. You could wish to find a route that requires the minimum effort. The route's minimum effort is the maximum absolute difference in heights between two consecutive cells of the route, depending on where you are. Return the minimum effort required to travel from the top left cell to the bottom right cell. I do know this one immediately. I think this might have been a recent, I don't know if it's recent contest or not, but either way, I think I would have gotten it the same way. I think just guessing the problem, I would have been like, oh, it's just, dynamic programming going from upper corner to right corner. But then here you're going to go up, down, left, right. And the general thing is that in dynamic programming, what you're looking for is some sort of a DAG. And what I mean by that is a directed asynchrotous graph, which means that you don't have any cycles. Is the short answer. And in this case, clearly, if you could go up, down, left, right, then you definitely have that. And here the effort is the maximum absolute difference in height between two consecutive cells. And here, it makes it a sort of a reachability problem, right? Which means that you look at it a little bit backwards. You have this example one where the maximum effort is going to be 2 because of adjacentness and stuff like that, and you can actually maybe plot or attempt to plot out the graph, but it doesn't go all the way. And actually it mentions it here. So then the idea is for me, and this maybe is just a lot of experience or a little bit of experience and a lot of practice, is just, and one common question that I get asked very often is, how do you know, right? And the short answer is I don't always. The short answer is that I think about it in my head. I go, can this be solved this way? And then I give it like maybe, how long it takes, if you watch my contest videos, like sometimes I spend a lot of time just thinking about it, trying to prove to myself. And sometimes I go immediately because I solved it before, or I have like a similar property that I've solved before. So then I'm like, oh yeah, this is true because I've solved this other thing, then that was true. So here, the key observation, the key thing to note is that, if there's an absolute maximum, if there's an effort of, well, one is that it's a minimization problem, right? And some part of this minimization, and it's not always true, but when the problem asks you to minimize, the first thing I would ask myself, maybe not the first thing, but like top 3 things, say, is I can ask, if k works, does k plus 1 work? If k plus 1 work, does k plus 2 work? And so forth, right? And you have this thing, and then you ask yourself maybe the opposite question as well, which is, if k doesn't work, does k minus 1 also doesn't work, right? And so forth. So you kind of try to figure out that way, and from that you basically have a Boolean array of, okay, yeah, false, 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 and then at some point it becomes true, and then it becomes true all the way through afterwards, right? And from here, you probably finally guess what I was hinting at, which is now you have a monotonic, a monotonicity property that which you can just basically do binary search on, and that's basically what we're going to do. I mean, after you come up with that, of course, I think this one I was a little bit confident, so I didn't even do that. But after that, of course, is that you look at constraints to make sure that this is true. Here, rows times columns, you go 100. So this is my off the bat thing. So I do 100 times 100. That's 10,000. And then you have height is you go to 10 to the 6. And in this case, that means that's the max. 10 to the 6 is always going to be a good answer because that's the maximum delta of the height, right? So then, you do log of that, which is, I don't know, what was it, 2 to the, let's say 15-ish? No, that's not even close. My math is terrible. 2 to the 20-ish? Yeah, so 2 to the 20, so that means that log of that is about 20. So here, this means it's equal to about roughly 200 something operations, so that's going to be good enough. That's my off the bat thingy. Obviously it's going to be a little bit rough, but that's good enough for me to be confident to move on. So now let's get started with the code. And also, yeah, I think I skipped some steps in explanation, but what I mean is that, okay, so how can you show that k is good enough, right, for a certain k? Well, then it becomes just a connectivity problem, right? Because let's say you have a graph, you have a graph that looks like this. Let's say you have a graph that looks like this. You can think of it as you think about a graph that is connected if given a certain k. Let's say k is equal to 10, just some big number. Well, 1 and 2 is going to be connected because it's less than 10 and so forth, right? And then now you change it to a smaller number. Let's just say 2. Well, 1 and 2 are connected, 2 and 2 are connected, but 2 and 8 are not connected because it is greater than 2, right? So that's basically the graph that we're going to, or, an implicit graph that we're going to keep on building for each one. And that's basically what we are going to do. And that's where the 100 times 20 came from earlier, because we're going to do 20 binary search, and each breadth first search is going to roughly take all of R times C, which is 100 times 100. I know that you also times like 4 for directions and the checks and stuff like that, but that's the big O roughly estimate, right? And also this is like what we said, 200,000. So like we have a lot of room of our margin, just a lot of room to work with. I would also say at this point, I know that there are conversations about binary search and templates and stuff like that. So definitely follow with me on how to kind of go to it. I don't usually do a template. I just ask myself the same questions every time, and that makes it easier. The only thing that you get to choose is whether the bounds are inclusive or exclusive. For me, I always choose to make them inclusive, and what that means is that we have a left and a right, and when it's inclusive, it means that both this and this are still in the consideration. And when they're at the same place, when these are on top of each other in the middle somewhere, like I guess this one actually, that means that your range is one element, which means that that's your answer, right? Because your range is one element, that means that you narrow the scope all the way down, right? So that's basically it. So left, let's just start with 0, because I think that's the most, that's the minimum. Like if the entire graph has the same number, then you want left to be 0. Or I think even in this case, but definitely when the graph is in the same number. And then on the right side, you can it's just probably actually the max of the heights. But in terms of just keeping it easy, I'm just going to do 10 to the 6, which is because that's the height of the bound. And technically, you can also say it's 10 to the 6 minus 1 if you want to be tight, but there are a lot of general, like the bounds are pretty generous, so I wouldn't worry about it. And again, as I said, when the left and the right collapses to one place because they're inclusive, we're in the right place, so we have left less than right, because when this is not true anymore, that means that the left is equal to right, and with left is equal to right, that means that's the answer. So we can even write just return left at the very end. So then we have just like standard-ish left plus right over the 2. I know that there's some overflow consideration, so in other languages you might have to write it differently. In Python, that's how we write it. And I may change this up a little bit depending on other stuff, but I just started writing this. And then now I write if good is equal to mid, and I'll write this good function later, but how do we want to define it though, right? Well, we want to define it as, if mid, if we can get from top left to bottom right with effort mid, right? So if this is good, what does this mean, right? So let's go back to, let's say we have this range and we have, this range all the way out here, middle is somewhere here, right? Say. So if this is good, what does this mean? Well, that means that we don't have to consider everything to the right because we know that this is already good. So that at the very least, like if everything to the left is wrong, this is the right answer, right? So that means that we want to set the right to the mid for this reason. And exactly the same way, if we're considering this point, we know that this is false, so everything to the left of this is false, and even the mid is false, because by definition it is false, so we could get rid of it, so then we could, the next iteration, we want to move it to the right of that. It's hard for me to do ASCII art, but yeah, but that's why you do left is equal to mid plus 1, right? This is not a template. I think about this on every problem, every binary search problem, and yeah, and that's basically the idea. And you could write like inverse functions and stuff like that to kind of get this to always be kind of similar, if not perfectly the same. But yeah. So now we have to write the good function, right? Oops, fingers in the wrong place. Let's just say target or effort, say that's the name. So as we said again, I'm going to copy and paste this because I'm a little lazy, tired, whatever. With minimum effort of, I wrote target because I'm usually call it target or X, but yeah, right? So this is just, and now this is more fundamental, which is what we talked about, implicit graph. So we're going to do a breadth first search. You can also do it with depth first search and stuff like that. Do I want to do, I guess it doesn't really matter, but I'm going to do it with a breadth first search with, and there's no cost in this one. Because it is binary, right? Like either you get to the end and you don't. So I'm just gonna put everything in a queue. Actually, I don't even have to put it. I could even use a stack, but let's just keep it consistent so that, because I think I think there are optimizations or changes that you can make, but I usually try to do it the same, like similar problems the same way as much as possible, so that I don't have to think about it, even if it's not necessarily like. I mean, in this case, it'll be optimal in the big O sense, but maybe, performance-wise, you could shave off like a little bit of a constant factor, but I'm not going to worry about it. It's fine, right? Like it's, especially on an interview, if you're able to talk about it later or even during, that's fine as well. So then now we append 0, 0. This is the top left corner, of course. So then now we just do exact, this is a breadth first search. Actually, we also want to put a scene. I'm going to use a set. I know that is a little bit inefficient. Technically, it's all one, but there are higher constants. What I would also recommend, if you're trying this at home, is doing a Boolean array, or a Boolean matrix in this case, because the rows and the columns and so forth. So you don't, so you could create a matrix already. Actually, I forgot about doing this. So let's do rows is equal to the length of this, and columns is equal to the length of heights of 0. Double checking that it has to be greater than 0, otherwise we should just check for it. It's not a big deal. But yeah, and what I always do is I have a directional directions array. And I write that roughly similar way. It's easy to see all the four directions. Definitely practice if you don't. But yeah. But now we get the the x and the y is equal to q dot pop left. And then if x is equal to rows minus 1 and y is equal to columns minus 1, we return true. Actually, I don't think I need to put this here. I could put this elsewhere. So I might do this later because you'll see why. So actually, let me just delete this. But yeah. And then now I write this roughly the same way. You may find other ways of writing it, and that's fine. You have to work on your own ways of finding what's good for you. But this for me is just getting the dx dy out the directions, and then here I just set x is plus dx, y plus dy, so that I get the next x and y, and then if the next x and y is equal to, or it's within the bounds, I write it like this in Python anyway. Yeah, and so now we know it's inside, and also we haven't seen it yet, right? Actually, let's do the other thing first, where we check the effort part, right? So heights of x, y, and we do an absolute value to check, minus heights of nx and y, if this is less than or equal to effort. And we also now want to check that we haven't seen it before, because if we've done it before, then we don't do it again. So then after, if all this is true, we put it in scene, and then we also put it in the queue. And here we can do one more thing, which is what we talked about earlier, which is if nx is equal to rows minus 1 and ny is equal to columns minus 1, we can return true early termination. And this is very standard breadth first search stuff. So yeah, so that's basically it. If you ran out of places to check, then you would just return false. I hope this is right. I mean, I think this is roughly right. Maybe I have silly mistakes here and there, but yeah. So let's put in, copy and paste the same one, I suppose. Oh no, this is slightly different, but let me see if I copy the right one. Oh yeah, I did copy and paste the right one, but yeah, let's run the code. Looks good. Let's give it a submit, cross our fingers. Uh-oh, is it too slow? Wrong answer. Huh. Oh. I mean, yeah. This is obvious why this is the wrong answer. I guess this is actually is funny because usually I do write the if xy here, and that would have fixed it. Yeah, I guess the other thing to learn is always keep on checking. But oh well, it's okay, because the trade-off here is that if I write it here, then obviously it fixed this case, which I just haven't considered, to be honest. But if I write it here, then it terminates a little bit earlier because you don't put them on the queue. So that it runs a little bit faster for that reason. But I missed an edge case as a result, and that was a trade-off that I made. As I was doing it. Sometimes I do it both ways. Sometimes I don't. I don't know. Let's give it a submit again. Yeah. Cool. Yeah, so what is the complexity of this? As I said, well, this binary search is going to be log of max height time. Let's call it h. So this is about roughly 20, say, because max h is like 1,000,000, as we'd said. And for each iteration, we do a breadth first search, which is linear, as you might know, which is r times c. Yeah, all of r times c for the complexity, and also all of r times c space. And you can maybe make some argument that if we reuse the queue in a good way, we could conserve the space so that it'll always be all of r times c. You can also debate about like garbage collection and stuff like that. So I'll let you to decide how that factors in. But in terms of, so this is for the good function. So in total time, so total complexity or time complexity is equal to be r times c times log h with total space. I'm just going to call it O of R times C. You can make some arguments on binary search and garbage collection and all that stuff. Yeah, so that's all I have for this problem. My new sign off is, actually I've been doing this on Twitch, but for whatever reason, I guess I just never did this on Leetcode, which is, I hope everyone has a great day, have a great week, had a great month. It's challenging times, obviously, still. The light hopefully is coming soon, at the end of the tunnel. Stay strong. I hope everyone stay healthy, to good mental health. Do good, not do well. I mean, do well too, but do good. And take care of yourself. And if you're fortunate enough to be in a good place, take care of the people around you. Treasure them, hug them, love them, and I'll see you later. Bye bye.